Hello grade 9s, welcome to today's Maths Lit video lesson. I hope you're doing well. Today we'll be covering what I believe to be the final section for grade 9 Maths Lit, probabilities for compound events, and you'll find this on page 299. After this we'll just be doing revision on all the work we've covered so far, try and solidify some of the concepts that weren't so clear when we sent out work during the lockdown, and after that we'll just be going over some past papers. In the previous video we looked at the probabilities associated with simple events such as flipping a single coin or rolling a single dice. If you recall, the coin had two faces, heads or tails, so the probability of it landing on any particular face is 1 out of 2. Similarly with the dice is a cube with the faces numbered 1 to 6, so the probability of it landing on any particular face is 1 out of 6. So here we're going to look at compound events. This is when we toss 2 or more coins or roll 2 or more die. If we look at the first compound event over here, which is where we flip 2 coins, we can see that it's made up of 2 simple events. We flip one coin and we flip another coin. It's important to note that the results of the first coin flip don't depend on or relate in any way to the results of the second coin flip. So these coin flips are random, and when this happens we say that they are independent. This contrasts to the case where the events depend on one another, and here we say that the simple events are dependent. So here we have a compound event looking at the four games of match performance for a soccer team. And so what sometimes happens is that a team will go on a winning streak or a losing streak. So for example, if the team has a big win in the first game, chances are they will go into the second game with a great deal of confidence and high spirits, and they might very well win the second game. So the results of the second game depended on the results of the first game. So they are dependent. Similarly, if a team has a very big loss, chances are they might go into the next game with low spirits and low confidence and not get such a good result. So the results of the second game might depend on the results of the first game. In grade 9 Maths Lit, the compound events we'll be looking at are all independent. We won't be considering any of the dependent cases. So in today's lesson, I'll be going over the worked example on page 299. I'll be going through each of the questions step by step. The workings are in the textbook, but hopefully if you follow what I'm doing, you'll be able to understand the problem-solving process a little better. Before we start, I just want to refresh you on how we calculate probability. Probability equals to the number of events that we're interested in over the total number of possible events that can occur. So if we look at the coin flip, and we're looking for the probability of getting a heads, there is only one of the faces with the heads, so the number of events is 1, and the total number of events that can occur, the total number of faces that can occur is either heads or tails, which is 2. So the probability of getting a heads is 1 over 2. Similarly, for rolling a dice, the probability of getting a 6 occurs on one of the faces, so the number of events is 1, and the total number of possible events is 6. Any of the 6 faces could come up. The first question of the worked example reads, what is the probability that when 2 coins are tossed, they both land with heads up? Explain. So we're trying to find the probability that we get a heads on the first coin and a heads on the second coin. So before we start, I just want to find the total number of possibilities that can happen. So now we're flipping 2 coins and we can get a number of outcomes. So I'm going to use what's called a tree diagram. and with each possibility there's a branch. So if we flip the first coin, we have the possibility of getting a heads for the first coin or a tails on the first coin. Now for the second coin, it's going to branch out from each of the possibilities from the first coin. So for the second coin, we can either have a heads or a tails, or a heads or a tails. So if we follow the branches of this tree, we can get the possibility heads, heads, heads on the first, heads on the second. If we follow the branch like this, we get heads on the first, tails on the second. If we follow the lower branch, we get tails on the first, heads on the second, and the last branch going like this is tails on the first, tails on the second. So how many possible outcomes do we have? We have 1, 2, 3, 4. So the total number of events is 4. The number of events we're interested in is just this one. Heads on the first, heads on the second, and that's 1 out of the 4. Another way of getting the total number of possible events is the multiplication rule. So we have 2 possibilities for the first coin, heads or tails, and we times it by 2 possibilities for the second coin. The second coin can also have heads or tails, and we get 4 possible outcomes. Question 2 reads, what is the probability that you will get a tail and an odd number if you toss a coin and throw a dice? So once again, I just want to list the total number of possible outcomes. If we flip the coin, we have 2 possibilities, heads or tails, and branching from each of these possibilities are the 6 outcomes we could get from rolling a dice. So we could get the numbers 1, 2, 3, 4, 5, or 6. And here as well, you get 1, 2, 3, 4, 5, or 6. So if we follow the branches of this tree, we get heads and 1, heads and 2, heads and 3, heads 4, heads 5, heads and 6. And if we follow the lower branch, we get tails and a 1, tails and a 2, tails 3, tails and 4, tails and 5, tails and a 6. So if we count the total number of possible outcomes, we've got 1, 2, 3, 4, 5, 6 plus another 6 is 12. So another way we could work this out is using the multiplication rule. We have 2 possibilities from tossing the coin. We could get heads or tails, and we have 6 possibilities from rolling a dice. The dice could land on any of the numbers 1 to 6. So 2 times 6 also gives us 12. In question 2, we are looking for the probability of getting a tail and an odd number. So let's count the number of events that we are interested in. So we're only focusing on the lower branch where we get a tail, and then we look for the odd numbers. So a tail and a 1, a tail and a 3, and a tail and a 5. So there are 3 events that we are interested in, and the total number of possibilities is 12. So the probability of getting a tail and an odd number is 3 out of 12, and this just simplifies to a quarter. Question 3 reads that a building site has 2 security guards at night to stop people stealing building materials. The guards are on opposite sides of the site and do not see or talk to each other. One of the guards is asleep on average half the time, and the other is asleep on average a third of the time. So I've drawn a little picture to help illustrate this. We have two guards on either side, and because they don't see or talk to one another, they operate independently. So for example, if this guy fell asleep, this guy wouldn't see him and wouldn't come across to wake him up. So we can let this guy fall asleep half the time and this guy fall asleep a third of the time. So the probability of the first guard falling asleep is a half, and the probability of the second guard falling asleep is a third. So if the first guard falls asleep half the time, then the probability that the first guard is awake is also a half. And if 1/3 of the time the second guard is asleep, the probability that he's awake is 2/3 of the time. The question asks, what is the probability that a thief will arrive when both guards are asleep? And because they both operate independently, we can use a tree diagram to work this out. In our tree diagram, we're going to have the branches for the first guard, and branching off from those possibilities are going to be the possibilities for the second guard. For guard number 1, the probability that he's asleep is a half, and the probability that he's awake is a half. Half the time he's asleep, so that must mean the other half of the time he's awake. For the second guard, the probability that he's asleep is a third, and the probability that he's awake is 2/3. So if he's asleep 1/3 of the time, he must be awake for the remaining 2/3. So this is for guard 2, and his possibilities branch out from the possibilities of the first guard. So we do our last branch here. The probability that the second guard is asleep is a third, and the probability that the second guard is awake is 2/3. So we have the outcomes that the first guard is asleep and the second guard is asleep. Then the first guard is asleep and the second guard is awake. Then we move on to the lower branch where the first guard is awake and the second guard is asleep. And the first guard is awake and the second guard is awake. So if we want to work out the probabilities for each of these events, we would multiply the probabilities for each of the branches. So for the first guard being asleep, it's a half, and we multiply it by the probability of the second guard being asleep, which is a third, and a half times a third is a sixth. For this branch, the probability that the first guard is asleep is a half, and the second guard is awake is 2/3, and if we multiply these, we get 2 out of 6. Same story for this branch, it's a half times a third, which is 1 out of 6, and for the last branch, it's a half times 2/3, which is 2 out of 6. So we are interested in the probability of them both being asleep, and that is 1 out of 6. So the probability the first guard is asleep and the second guard is asleep is 1 out of 6. Notice that if we add together the probabilities of all possible outcomes, we will be adding 1 out of 6 plus 2 out of 6 plus 1 out of 6 plus 2 out of 6, and that will give us 6 out of 6, which equals to 1. So there's 100% chance of either of these events occurring, and we say that we've exhausted all possibilities. Similarly, we can think of the case when we're flipping a coin. The probability of getting a heads is a half, and the probability of getting a tails is a half. And if we add up these probabilities, a half plus a half is 2 out of 2, which is 1. So we've exhausted, once again, all possible outcomes. With a coin flip, we can either get a heads or a tails. For the final question, question 4, we organize the information according to this table. So they give us that there are a total of 20 learners. They also tell us that 7 wear glasses. So if we look at the number that wear glasses, the total is 7. And it also tells us that 4 of them are left-handed. So the total of left-handed is 4. Lastly, they tell us that 2 of the students are both left-handed and wear glasses. So we would put the 2 here. This intersects the column of left-handed with the row of glasses. They intersect here. With this information, we can now fill in the remaining values. It's a little bit like Sudoku. So if we have a total of 4 left-handed students, then the number of right-handed students must be 16, because 4 plus 16 gives us a total of 20 learners. And similarly, if we go down this way and we're looking at the split between glasses and no glasses, there must be 13 with no glasses, because the 7 and the 13 must give us 20. Along this row, if there are a total of 7 with glasses and 2 of them are left-handed, then the number of glasses that are right-handed is going to be 5. And if we look at this column, if there are a total of 4 left-handed students and 2 of them have glasses, then 2 of them don't have glasses. 2 plus 2 must give us 4. And for the final value across here, the number of no glasses that are left-handed is 2, and the total number of students with no glasses is 13. So the number of right-handed students with no glasses must be 11. So 2 plus 11 gives us 13. We can use the information from this table to answer the following questions. Question 4b asks to calculate the probability that if you pick any one of the 20 learners at random, they will, and 4b number 1 is asking the probability that they will be right-handed. So you're picking from 20 learners, that's the total number of events. The number of events we're interested in is right-handed, and there are a total of 16 right-handed students, so our probability is 16 out of 20, which simplifies to 4 out of 5. Question 4b2 asks for the probability that the students will be right-handed and not wear glasses. So here is the column for right-handed and no glasses. That intersects by the 11. So the number of events we're interested in is 11, and the number of possibilities, the number of students we pick from is 20. So our probability is 11 out of 20, and that doesn't simplify further. Question 4c reads, what is the probability that if you choose one of the left-handed students, they will be wearing glasses? So So this differs slightly from question 4b in that we're only picking from the left-handed students. The number of left-handed students is 4. So that's going to be the total number of events, the total number of possibilities we can pick from, the 4 students which are left-handed. And the number of events we're interested in is for wearing glasses. So the number that are left-handed and wearing glasses intersects at this 2. So the probability is 2 out of 4, which simplifies to a half. So that concludes today's video lesson, and we're also done with the section on probability. Lastly, I'm going to do exercise 25.2. I'm not going to make a video on the solutions for this. Instead, I'm going to do handwritten ones and send them out. And your job will be to watch this video, read the textbook, and figure out how to do these problems on your own. So thanks for watching. I hope you understood. Probability is either dead easy, dead certain for some, or completely impossible for others. Thanks for watching and take care.